All right, well, welcome back. So for those of you that actually had class with me before, you may notice that my screen looks a little bit different. Over break, I actually upgraded to an iPad Pro that allows me to make use of this fancy little Apple Pencil to nicely doodle and change colors and highlight and do all the nice things that Apple likes to shove into their tablets. Unfortunately, my ability to draw is still pretty terrible. Even with, $1,000 tablet, my ability to sketch out even a reasonable picture of Alice and Bob and Eve is still pretty rubbish. So you're gonna end up getting these nice little stick people. Bob's still gonna have a nice little top hat. Alice is going to be Western wear wearing, so she's got her cowboy hat. And Eve, the evildoer in the middle, is typically still going to be wearing a witch hat, all of which are going to still be poorly drawn. So anyways, we'll jump back into the world of cryptography. So last semester, we actually saw that this invention of the Diffie-Hellman key exchange, as well as the RSA public key crypto system, both of the 1970s, actually kickstarted a massive effort to begin studying a lot of these classic, quote unquote, hard problems that actually underlie these systems. So to kind of refresh your memory, we know that this Diffie-Hellman key exchange is going to be based on the discrete log problem, and then the RSA public key crypto system is going to be based on integer factorization. The idea is that if we have a nice and fast way to factor this modulus n in RSA, then we know that we can easily read any message between Alice and Bob. So Eve has this kind of sneaky trick that, she can record the n, factor it down, know what P and Q are, easily achieve whatever Alice or Bob's keys are going to be, and then can read any communication that's going to be sent between the two. So the very obvious thing that we want to do is we want to constantly think about developing new types of crypto systems. Ideally, these things are going to be based off of other, hopefully, quote-unquote, hard problems. We don't want to make everything based off of integer factorization, or we don't want to make everything based off the discrete log problem, because once we have an ability to attack one of those things, so the idea is that quantum computing and Shor's algorithm and all of those things, those immediately break something like RSA. So we constantly want new things that are going to be based off of other types of hard questions. And that's going to be the big goal of this semester, is we're going to be studying a variety of different kind of extensions beyond the classic 1970s. We're going to be living in the world of elliptic curves, and we're going to be looking at error correcting codes, a little bit of lattice theory, a bunch of other proposals that are going to be living in different camps. So we get some security based on things that are not so interconnected, which is a really nice thing. So we're going to have this semester essentially broken into 3 big chunks. We're going to start off looking in the world of elliptic curves and hit this really hard and see all of the underlying guts of it. And then we'll move into a few other bins. So to give you a really quick kind of background on the world of elliptic curves, they're actually been around for forever, but it was in the 1980s, I think it was about 1985, that Neil Kolowitz and Victor Miller actually independently proposed using these elliptic curves to create crypto systems. They actually suggested that an analogous elliptic curve discrete log problem, so again, remembering Diffie-Hellman is based off of the classic discrete log problem, elliptic curves are going to have another problem that has that name, but it's going to be very different. But in any event, with an elliptic curve discrete log problem, we actually are able to develop a few other things that are maybe more difficult than the classic discrete log problem. In fact, a lot of these public key exchange and public key crypto systems that are going to be implemented using elliptic curves are going to require smaller keys and run more efficiently than, let's say, RSA. For example, a 4096-bit key size in Diffie-Hellman can actually be replaced by a 313-bit elliptic key crypto system. So we can see that there's a really nice shrinking of size and information that we have to store. So because of this, elliptic curves have actually played an increasingly important role in many cryptographic situations. We're a little bit later going to see how some of these things can be retooled into the world of things like Bitcoin, and they seem to creep in a lot of other areas. So in this topic, we're going to be digging into all things elliptic curve related. So we're going to be starting off by looking at the general structure of elliptic curves and then move into elliptic curve crypto systems and a variety of other applications. So along the way, I'm going to be inserting a little bit of history as well as some fun extensions of this really truly fascinating field. So note that this area of elliptic curves is truly massive, so we are unfortunately going to be restricting ourselves only to those problems and questions that are actually going to be related to cryptography. So anyway, let's go ahead and dig into what this kind of world of elliptic curves is all about. So an elliptic curve is simply going to be a set of solutions to an equation of the following form. So you're going to have a y squared, which is going to be an x cubed. So notice that it's cubic on the right-hand side and quadratic on the left-hand side. And then we're going to have this ax plus b. Later on in some of the activities or homeworks, I'm going to show you that if you put a quadratic term, you can do some fancy little factoring and you can change some things up to actually put them in this form. But the classic representation is going to be given by something like this. A and B are allowed to be positive or negative or even zero, so you're going to see a variety of different shapes and structures that are going to emerge from this. This section is primarily devoted to looking at these things over the real line. Naturally, we're going to begin restricting ourselves to the integers and ultimately to the integers modulo some number p. So that's where the elliptic or the discrete version of these elliptic curves are going to come into play. So in any event, down at the bottom we have a collection of these things just to kind of showcase that you can have negatives, you can have positives, all kinds of different things you can shove for A's and B's. It is worthwhile to begin looking at some of the pictures because that's where the kind of meat of this whole structure is going to be living in. So the first thing you can see is right off the bat that these elliptic curves are not functions. So they fail at this vertical line test. We're going to have the kind of x value is going to actually go to possibly two different y values. You can see at this point for 0 for x, it's got one y option and then another y option, which makes sense because it's coming from a y squared term. So that's one of the things to notice is that it is in fact not a function, but we get a lot of things that are going to be related to functions out of it because you could essentially solve this for y and you get a plus or minus situation. So you can do a lot of those things that you're used to from college algebra and things like that. You just got to take a little bit more care when you're working with it. So the thing you can see right away between these two, and they look very similar, we have x cubed minus 6x, so x cubed minus 6x. The only thing I've changed is I've put a plus 20 over here and a plus 4 over there, and you can see that this elliptic curve went from being a nice connected, almost puzzle piece shape, into something that's actually disconnected. So there's this little loop over here on the left, and then there's this kind of big slanty V thing. You can also see that sometimes they make a slightly flatter puzzle shape. So this one x cubed plus 17. So I actually have an a value that's a 0. And then also we have some kind of unfortunate situations that can emerge over here. We can sometimes get some weird double crossings. For example, if I have something like a -3 for my a value, and then positive 2 for my b value, you're actually going to get this double crossing that's going to happen here. And these types of elliptic curves are actually going to be things that we want to avoid. What's going to be problematic there is that I'm not really sure if I'm taking the first point in the crossing or the second point. There's a little bit of unknown. So these types of elliptic curves are going to be referred to as singular. So they're going to be ones that we're going to want to avoid. And in a little bit, I'm going to give you a way to easily identify whether or not something is singular. It's actually based on an interplay between that A and B value. So it's a really easy test to see whether or not something is truly bad. So back on this first slide, I actually have a link to a Desmos page, which if I can nicely play. So here's that first one, this x cubed minus 6x plus 20. It's got this classic puzzle piece shape. But what you can do here is you can click on something like this, and let's turn off all the other stuff that I have happening here. So off, go off, go off, go off. All right, so you can see that I get this nice little shape, and if I put this into projector mode, we should be able to see it a little bit nicer. Let's undo some of those labels too. All right, so what's happening here is that that's actually that singular one where A is -3, B is 2. The little value that's going to identify that being bad is this quantity 4a cubed plus 27b squared. But what's nice about this is you can play with these little sliders and you can kind of see that you sometimes get a connected one, you get a disconnected one, you can see how they can be reconnected, all kinds of kind of interesting fun shapes that exist in this world of elliptic curves. So like I said, it's a massive area with tons and tons of connections into the world of geometry. we are primarily going to be sticking in the applications that are related to cryptography. I should make note that they are called elliptic curves, though very obviously they are not ellipses, so thinking of ovals and things like that. They actually get their name from something that's referred to as an elliptic integral that actually emerges when you try to compute the arc length of a given ellipse. So for those of you that have taken a little bit of calculus, you've probably seen this formula for computing arc lengths. They have some horrible square root, and if you start with an ellipse and do a little bit of differentiation, you're actually going to see quantities like x cubed plus ax plus b emerge. And that's actually the connection as to why we're calling them elliptic curves. But anyway, we're just going to call them elliptic curves. Kind of just realize that they're not ellipses is the big take-home message, but realize that with this entire section, there is always going to be this beautiful underlying geometry side of things. We're just going to constantly know that that's a really cool area, but we're not going to be kind of fully diving into that as much because we want to get at the really nice meaty cryptography stuff.